Hey guys, my name is IBM, and today I would like to take you into this is going to be oscillations. Do not forget to subscribe if you want. You do not forget to write your comment. I'm always willing to try my level best and rectify whatever is not clear. I'm always ready to answer questions. I'm always ready to take constructive criticism, and I don't mind really much about your most of your negative comments. So you're free to enjoy the videos and you're free to write your comments as you wish. So today I want to take you through oscillations, and I would like to take you through oscillations, and I think this is going to be most probably one lesson, I think. But before we talk about oscillations, of course, we cannot really draw a boundary between oscillations and simple harmonic motion, because simple harmonic motion is one type of oscillation that we shall later on classify as free oscillations. So we cannot really draw a boundary between oscillations and simple harmonic motion. So, but we recall the concepts of simple harmonic motion, where we mentioned that the oscillations were periodic, or the motion was periodic, meaning that it went on forever and ever. So it means for simple harmonic motion, we would assume that oscillations would occur indefinitely. But of course, in practice, we are going to see that they may not really occur indefinitely. So we are going to explore the types of oscillations, which are basically going to be three. We shall talk about free oscillations, damped oscillations, and forced oscillations. And of course, we shall talk about damping, and then this unit will really be, it will actually be done. So let's start by understanding what we mean by oscillations. What is an oscillation? I think we somehow defined an oscillation under simple harmonic motion, but we shall still redefine it here for learning for examination purposes. So what is an oscillation? So when someone talks about an oscillation, as indicated by these animations, you notice that there is always a to and fro movement of objects as demonstrated by these animations. Therefore, we can always talk about this to and fro, back and forth movement of an object as being oscillation. So an oscillation is entirely going to be a complete to and fro movement of an object. So in an exam, you can define an oscillation as a complete to and fro movement of an object. These animations are all showing that the object moves back and forth. It moves towards and forwards. I mean towards and backwards. That's what we call a to and fro movement of an object. That's what we are going to call an oscillation. It's a complete to and fro movement of an object. That's what we call an oscillation. So oscillations exist in three types, as I've already mentioned, and these types are going to be free. We are going to have what we call damped, and we are going to have what we call forced oscillations. So what is the difference between these three? Free, forced, and damped oscillations. Let's see the difference between the types of oscillations. But from this slide, I want us to be sure that we can define an oscillation as a complete to and fro movement of an object. That is what we call an oscillation. And all these animations are demonstrating what we mean by an oscillation. For example, if I consider this animation starting from this point, it it goes to the extreme point upwards. Let's say up to this point here. So if it starts from A, it goes to, if it starts from this, let's say this is A, and we're going to call this level B. It starts from A, it moves to B. If it comes back to A, then we call that a complete oscillation, a complete to and from. We start from A, we move to B. The moment we come back to A, we shall call that a complete oscillation. Similarly, in this animation here, if we start from this point and we move to the other point, we start from A, for example, move to B. The moment we move from A to B and back to A, that is considered to be a complete oscillation. So that is a complete to and from movement of an object. That's what we call an oscillation. Okay, so let's see the types of oscillations. So oscillations, I've mentioned they exist in three types, or we shall explore three types of oscillations. Number one is going to be free oscillations. Number two will be maybe damped oscillations. And number three, we have what we call forced oscillations. I'll begin by giving a simple explanation. If you pluck, for example, a guitar string, if for example you pluck a guitar string, it continues to vibrate for some time after you have released it. It vibrates at a particular frequency, which we shall later on call the natural frequency of vibration. Natural frequency. You pluck it and leave it to vibrate on its own. Therefore, the frequency with which it vibrates when you are not continuously plucking it will be called the natural frequency of vibration. And it gives rise to a particular note that our ears can detect. In the same way, if you hit the pongs of a tuning fork, I think every laboratory has a tuning fork. If you hit the pongs of a tuning fork, the tuning fork vibrates with a natural frequency. Most of those tuning forks have frequencies labeled on them. So it's like you give them an initial disturbance and then they continue vibrating on their own. So we say they are vibrating freely. If there was no loss in energy, then we would expect them to vibrate indefinitely. We would expect them to vibrate or oscillate indefinitely. But because of the natural forces such as air resistance and other kinds of forces in the environment that we call dissipative forces, they may end up losing their energy. So the simple harmonic motion that we have been considered, where we consider the amplitude to be constant, it means there was no energy lost and there was no energy gained from the surrounding. So the oscillations continued indefinitely and the amplitude remained constant. For such oscillations where the amplitude remains constant, no energy is gained or lost to the surrounding, the oscillations continues indefinitely, we call them free oscillations. So simple harmonic motion that we have talked about is an example of free oscillations because the oscillations are expected to continue indefinitely with a constant amplitude, with no loss or gain in energy. No external influences occur, no dissipative forces are considered in this case. So for such oscillations, we call them free oscillations. The most important factor here is that there is no loss or gain in energy. And because there is no loss or gain in energy, the amplitude of oscillation remains constant. That's why we call them free oscillations. So the simple harmonic motion that we considered is an example of free oscillations. But remember, the examples of simple harmonic motion that we gave were just systems that were approximating simple harmonic motion. They were not actually simple harmonic motion. Because if you displace a simple pendulum and leave it with the time, the amplitude of oscillation goes to zero, meaning we shall have what we call damping that we shall explore in more details later on. So one type of oscillations, we have the free oscillations where the amplitude of oscillation remains constant because oscillations are occurring with no loss or gain in energy. But of course, in practice, systems do not oscillations of systems do not actually occur in the absence of dissipative forces. There are natural dissipative forces existing in the environment. And these dissipative forces affect the oscillations of these systems, resulting into either a gain or decrease in energy. And if it is a decrease in energy, it is going to result into a decrease in amplitude of oscillations, and therefore such oscillations are going to be said to be damped. These are going to be damped. So damped oscillations are going to occur with a decrease in amplitude. The amplitude of oscillation decreases. And the reason as to why it decreases is because there are dissipative forces such as friction, it could be air resistance, which reduce the energy of oscillations. So it's like damping involves loss in energy of oscillations, loss in energy of oscillations, which results into decrease in the amplitude of the oscillations. The reason as to why the energy of oscillation is reduced is because there are dissipative forces. These dissipative forces always act against the direction of motion of the oscillating object, such as air resistance. You notice that air resistance, for example, always acts in the opposite direction to that of the speed or that of the velocity of the moving object. So another type of oscillation would be damped oscillations, which occur with a decrease in amplitude due to dissipative forces such as friction, air resistance, which reduce the energy of oscillation. Then the other type of oscillation which I'll talk about is going to be forced oscillations. These ones are forced oscillations, and what do we mean by forced oscillations? So we shall of course explore forced oscillations in more details at the end of this unit, but just to give you a hint, imagine you are in a bus and the engine of the bus is started. When the engine of the bus is started, your body starts vibrating, and when the engine of the bus is turned off, your body stops vibrating. So it means your body was actually vibrating at the frequency, or it was being forced to vibrate because of the vibrations of the engine. It was not vibrating on its own, and when the engine is switched off, your body stops vibrating. Therefore, it means forced oscillations occur by continuous energy input by an external periodic force or driving oscillator. There is an external driving force which gives our system additional energy to continue vibrating. So forced oscillations occur by continuous energy input by an external periodic force or driving oscillator. In this case, in the case or in the example of um, the bus is the external is the driving oscillator or the external driving oscillator which continues on supplying energy to your system or to your body, which your body is going to act as the driven system, and your body is going to be forced to vibrate at the frequencies of the engine of the bus. So those are what we call forced oscillation. So there are three common types of oscillations that we are talking about here. Free, there is no gain or loss in energy, amplitude remains constant. Damped, there is loss in energy because of dissipative forces, the amplitude decreases. Forced oscillations, these occur by continuous input of energy. So if the energy input is stopped, the oscillations also stop. These are what we call forced oscillations. So these are the three types of oscillations we are going to explore in this unit. Let's start with the free oscillations and explore them in more details. Free oscillations. So let's talk about free oscillations. The animations on this slide indicating free oscillations because they will not stop. The oscillations are occurring indefinitely. They are not even stopping. The amplitude of oscillations is remaining the same simply because there is no loss or gain in energy. So what is very important for us to note with the free oscillations is that there is no loss or gain in energy for free oscillations. And in simple harmonic motion, remember, by the one example of free oscillations, I say the simple harmonic motion is an example of free oscillations. Remember the energy of a body performing simple harmonic motion was given by a half m omega squared times x naught squared. This was total energy. And if there is no loss or gain in energy, it means E naught is constant. Of course, mass is already constant. omega is constant, it also means the amplitude of oscillation must remain constant. So no loss or gain in energy, which means the amplitude of oscillation remains constant as time goes on. So we say there is no damping. So it's like free oscillations, there is no damping. And we shall understand what we mean by damping. So this type of oscillation will only occur in theory. So that's why I said under simple harmonic motion that the types of motion that we considered in simple harmonic motion were simply systems that were approximating simple harmonic motion. They were theoretical. In practice, those systems could come to an end. The oscillations of those systems would stop because they were simply theoretical. So they were just ideal illustrations. In practice, there will always be some damping. In other words, there will always be some loss in energy of the oscillating system. And if the energy of the oscillating system is lost, as we are going to see, the system or the amplitude of vibration goes down to zero and the system stops oscillating. So because for free oscillations, the amplitude does not change. If we were to sketch a graph of displacement against time, the amplitude would remain constant throughout the motion. The system vibrates to the same maximum displacement throughout the motion. So this is a graph of displacement against time. This is a graph of displacement against time for a system which is undergoing free oscillations. The frequency of oscillation, of course, is constant. The amplitude is constant. The energy of oscillation is constant. There is no loss or gain of energy. So the frequency with which a system oscillates, if it is oscillating freely with no loss or gain in energy, is going to be called the natural frequency of oscillation. So the frequency of oscillation is going to be called the natural frequency of oscillation. Each object has its natural frequency of oscillation. The examiner will ask you to define what we call the natural frequency of oscillation, and I have defined the natural frequency of oscillation for you here as the frequency with which a body vibrates when free to do so with no gain or loss of energy. The last part is the most important part. There's no gain or loss. There's no gain or loss of energy. There is no gain or loss of energy. That is simple natural frequency. The frequency with which a body oscillates or vibrates when free to do so with no gain or, this is all, loss of energy. That's what we call the natural frequency of vibration or the natural frequency of oscillation. So free oscillations have a frequency which we call the natural frequency of vibration, and these occur with no loss or gain in energy. That is what we call free oscillations. But like I have said, we have considered simple harmonic motion to be free oscillations whose amplitude remains constant, but that was simply theoretical. It was not really practical. We could say it is a practical ideal. So, in other words, the oscillations of a body or system with its own natural frequency and under no external influence other than the impulse that initiated the motion is what we are going to call free oscillations. An object is given an initial impulse or initial disturbance and it is left to oscillate on its own with no loss or gain in energy from the environment. And therefore, the oscillations of that object are going to be called free oscillations. There is no external influence, no gain or loss in energy. The frequency is going to be called the natural frequency. The body oscillates with the constant amplitude and no loss in, since there is no loss or gain in energy. Such oscillations are called free oscillations. I said a good example could be a free pendulum as shown here in this animation, but unfortunately in the laboratory, when we set up a simple pendulum in the laboratory, we notice that with the time the amplitude is, the pendulum stops oscillating, which means it wasn't really a free oscillation. But at the start, it appears as if it is a free oscillation because you give it an initial disturbance or displacement and you release the pendulum to oscillate on its own as shown in this animation. But with the time, in the laboratory, you would notice that the pendulum comes to a rest, which means it was not really a perfectly free oscillation. So simple harmonic motion was considered or is predicted to be as free oscillations, but it is really just an ideal situation. It cannot remain free indefinitely. So that is the free oscillations. I think we should now talk about damped oscillations. Let's talk about damped oscillations. You should be able to define free oscillations and the natural frequency of an oscillation. So to understand the meaning of damped, let's consider a simple situation where a mass is initially given a mass attached on a string is initially given a disturbance. In principle, oscillations can go on forever. That is, in principle or in theory, oscillations like those of simple harmonic motion can go on forever. But in real situations, however, there are factors such as friction, air resistance, and other resistive forces which cause the oscillator's energy to be dissipated. This energy is normally converted into heat or thermal energy. That is in real situations. So in principle or in theory, we can assume that some oscillations like simple harmonic motion go on forever. But in real situations, the ones we observe in the laboratory, like with a simple pendulum or with a mass oscillating on a spring, we notice that in real situations, friction, air resistance, and other resistive forces cause the oscillator's energy to be wasted as heat or to be dissipated into other forms such as heat. In that case, we say that the oscillations are being damped. So it's like damping is produced by resistive forces which dissipate the energy of the vibrating system. So in real situations, oscillating systems can easily be damped. They are always damped by dissipative forces which waste or make them lose their energy of oscillations. So that's what we are going to call damping. So we defined damping earlier on, or damped oscillations as oscillations to occur with a decrease in amplitude due to dissipative forces such as friction or air resistance, which make the system lose its energy. So such oscillations which occur with a decrease in amplitude are going to be called damped oscillations. They occur with a decrease in amplitude because the system loses its energy, since energy is equal to a half m omega squared x naught squared. This is the total energy. Because the system loses its energy as heat, the amplitude of oscillation also decreases. Those systems are going to be damped. So if we were tempted to sketch a graph of, displacement against time, then we would sketch the graph with a decreasing amplitude, but of course the oscillations could continue or there could be no continuous oscillation. So there are going to be types of damping. In this slide, I've demonstrated one type of damping, which is going to be called light damping. This is called light damping. So in this animation represented with a spring, the spring is given a displacement, but because of maybe air resistance, the amplitude of vibration goes on decreasing, as demonstrated by this animation here. The amplitude of oscillation goes on decreasing, as demonstrated by this animation here. But the frequency is remaining the same. The frequency is not changing. The frequency or the period is not changing. So the time of one cycle is actually remaining the same, but the amplitude of oscillation is decreasing. So if the amplitude of oscillation decreases gradually, as demonstrated by this animation here, we say that the system is lightly damped. So this is called light damping. So we say the system is lightly damped. And if you were to sketch an envelope around it, you notice that the decrease in amplitude is is exponential, it is gradual. So normally resistive forces are present to damp the motion. Commonly it is air resistance and friction. So normally it is air resistance and friction. If it is in a liquid, it could be called viscous drag, or it could also be called friction between the liquid molecules and the surface of the container of the liquid, or the container containing the liquid. That could still be friction. Instead of saying friction between the water molecules or the liquid molecules, you could say viscosity or viscous drag between the water molecules. That could cause maybe damping if the oscillations are in a liquid. So commonly it is resistance or friction, and mechanical energy is lost and it is transformed into internal energy of the air molecules. If it is air resistance, it could be turned into internal energy of the water molecules if it is in liquids. And this is basically going to become thermal energy or heat. So the amplitude of oscillations decreases, and that's what we call damping. But this first type of damping we have elaborated here is going to be called light damping, or the system is going to be lightly damped. So what is unique about light damping? Number one, for light damping, the system continues oscillating. The system continues oscillating, but the system continues oscillating with the amplitude decreasing gradually. That is for light damping. The system continues oscillating. For light damping, oscillations are still continuing, but the amplitude decreases gradually. That is exactly what happens if you displace a pendulum bob in air in the laboratory. That is, if you are dealing with a simple pendulum. This is the same situation if you displace a mass attached on a spring, as demonstrated by this animation here. The amplitude gradually decreases due to dissipative forces, which waste the energy of the oscillating system. The dissipative forces use up the energy of the oscillating system, and that's what we call light damping. Okay. The other type of damping, we are going to discuss three types of damping. The first one was light damping. The other one is going to be heavy damping and over damping. Critical damping. So this one is the amplitude decreases exponentially as shown by this graph here. The amplitude gradually decreases, that is light damping. The other type of damping is going to be called the heavy damping. So we have heavy damping and critical damping. So what is special about these other two types of damping? Unlike light damping where oscillations continue, for heavy damping and critical damping there are no oscillations. For heavy damping and critical damping there are no oscillations. For the case of heavily damped or heavy damping, no oscillations occur and the system returns very slowly to equilibrium position. In other words, the amplitude goes to zero without oscillations, but it takes a long period of time for it to tend to reach zero. The amplitude decreases to zero, but with no oscillations, but it will take a long period of time to reach zero. For example, if you leave a spring on a rough surface, or you stretch a spring on a rough surface and release it, because the surface is rough, the spring may go back to its unstretched position, but over a long period of time, because its energy is being wasted to overcome the friction between the spring itself and the surface, which is rough. So that's what we call heavy damping. But if you have entered in some offices where there is a door that has been damped, when you pull the door, you can easily enter the room without minding about closing the door, because to close itself, since it has been heavily damped, it takes some time to close itself because it has been heavily damped, but there will be no oscillations and it will not overshoot the closed position. So The other types of damping are going to be heavy damping and critical damping. Heavy damping is sometimes going to be called overdamped. If a system is overdamped, there is no oscillations. There will be no oscillations in that case, but the system, its amplitude decreases to zero, but over a long period of time. So here the oscillating object is placed in a very viscous medium. That is, if it is in a liquid, we talk about viscosity. There will be no oscillations occurring in that case for heavy damping, but the object displaced takes a long time to return to its rest position. That's what we're going to call over damping. Another example is that many office doors, or when you go to banks, you notice that many office doors or bank doors have been heavily damped. There is a machine they put on top of the door or on the sides of the door that when you open it, you don't mind about it. When you enter, it will come to its closed position gradually after some time. So they have been heavily damped. That is what we call heavy damping. Then let me first go back slightly. The other one is critical damping. I want to also briefly talk about critical damping. The other type of damping is the critical damping, which I've just showed here. What is special about critical damping then? And what distinguishes it from heavy damping? For critical damping, when you compare the graph of displacement against time for both heavy and critical damping, you will notice that for critical damping, still there is no oscillations. No oscillations occur with the critical damping. But for critically damped motion, the time taken for the displacement to become zero is very small, is minimal. The system reaches equilibrium position as fast as possible without oscillating. Experiments have shown that this time here, the time taken for the system to return to equilibrium position for critically damped is approximately a quarter of a cycle that it would take if there was an oscillation. If the system was to oscillate, and it would take a time t to make one oscillation. Then for critical damping, the time it takes to reach zero is approximately a quarter of the period. So critical damping causes the displacement to reduce to zero in the shortest time possible without any oscillation of the object. And these experiments have shown that this time is approximately a quarter of a period. That is, if there were oscillations or if oscillations were to occur. That's what we call critical damping. So for critical damping, the system returns to equilibrium position in the shortest time possible, which is approximately a quarter of a period. And remember, period is equal to pi over omega. So it means the shortest time for critical damping, the time is going to be a quarter of that, which would be pi divided by twice omega, where omega is the angular frequency or angular velocity. Angular velocity or angular frequency. So that is critical damping. The system returns to its equilibrium position in the shortest time possible. Okay, so a few things you must have noted from what we have discussed. These include the following. Number one, we now know what we mean by damping. The system, under the influence of dissipative forces, loses energy of oscillation, resulting into a decrease in amplitude. So damping is the loss of energy by an oscillating system due to dissipative forces. This one is leading to decrease in amplitude. Whether it is light damping, heavy damping, critical damping, all dampings are resulting into decrease in energy. That is damping. Loss of energy by an oscillating system due to dissipative forces leading to decrease in amplitude. Then we have three types of damping. We have lightly damped. Lightly damped is sometimes going to be called underdamped. Here oscillations continue, but they continue with a gradual decrease in amplitude. That is light damping. Then we have critical damping. Critical damping, here there are no oscillations, but the amplitude reduces to zero in the shortest time possible without any oscillations. And we say that the time here is approximately equal to a quarter. It is just approximately equal to a quarter of a period. That's what we call critically damped. We also have overdamped or heavily damped. Still, there are no oscillations for heavy damping, but it causes an exponential reduction in amplitude over a greater time than for critical damping. So the amplitude decreases to zero over a longer period of time compared to critical damping. And that's what we call heavily damped or overdamped or overdamping. So we can now compare the three types of damping on the same scale or on the same axis. So there are basically three types of damping which are going to be summarized in this graph. So we have light damping represented in red, where the amplitude decreases gradually to zero, as we see from this graph. Then we have heavy damping, where the amplitude goes to zero but reaches zero over a longer period of time. And we have critical damping, where there are no oscillations, but uh, this is going to be approximately a quarter of a period if the system was to oscillate. So the amplitude decreases to zero in the shortest time possible, which is approximately or very close to a quarter of a cycle. And these animations here, besides, are demonstrating what we call overdamped. Overdamped, that is heavy damping. Then we have critically damped, that is critically damped. Then we have underdamped. Underdamped, that is light damping. So you notice that for both overdamped and critical damped, oscillations do not occur. But for light damped or underdamped, this is light. The oscillations occur, but the amplitude gradually decreases with time. That's what we call the three types of damping. For overdamped, the systems do not oscillate, but critical damping reaches equilibrium position or the amplitude goes to zero in the shortest time possible. For light damping, the amplitude goes on decreasing, but the oscillations continue for some period of time. Those are the three types of damping. Damping is the loss in energy of an oscillating system due to dissipative forces resulting into a decrease in amplitude, and that is damping. Okay, let's briefly explore some applications of damping, or especially critical damping. We have already mentioned heavy damping. You find heavy damping normally in office doors, on office doors and bank doors. Let's talk about some of the applications, even though they are not really very important for this curriculum. So for critical damping, like we have mentioned, the object displaced when released returns to equilibrium position without overshooting and in the shortest possible time. No oscillations occur, as we have mentioned. The most common use for critical damping is in moving coil meters. For example, you have seen an ammeter. When you connect to a power supply, the pointer immediately moves. When you connect a galvanometer, a voltmeter, those are the analog instruments to a power supply or a battery, the pointer immediately moves because it is critically damped. When you turn the switch off or when you disconnect, the pointer immediately goes back to zero because it is critically damped. So moving coil meters such as the analog meters, the analog voltmeters, the analog ammeters, the analog galvanometers use critically damped. They are made up of an electromagnet, which it becomes a magnet immediately when a current flows through it, and it loses its magnetism immediately when the current stops flowing. So it is critically damped. We also have what we call suspension systems of cars, which we wrongly call shock absorbers. A good car suspension is one in which the damping is lightly under critical damping, as this results in a comfort ride and quickly leaves the car ready to respond to further bumps in the road. So for for shock absorbers or for suspension car suspensions, critical damping is very important. So the shock absorbers are designed with a spring, which spring is going to help in which spring is going to control the damping here. That when the car runs over a bump, this immediately goes back to equilibrium position. The amplitude of oscillation immediately goes back to zero without oscillation, so that in case there is another bump ahead, the car can be stable, it doesn't lose stability. So suspension systems of cars, which we want to call shock absorbers, these ones have been critically damped. Some of them are heavily damped, others are critically damped. Moving coil instruments, these ones use critical damping. I've said moving coil instruments include the voltmeters, the ammeters, those are the analog instruments. Okay, so a good example of damping can be seen in moving coil galvanometer. Those are the moving coil instruments that I've been talking about. What is inside the galvanometer that makes it damped? I've mentioned that the galvanometer or even the analog meters, they have an electromagnet. An electromagnetic damping is used here. The coil moves in a magnetic field and the current flowing in it can be shorted with a resistor, thus varying the damping. So what is inside these moving coil meters is basically an electromagnet, which automatically becomes a magnet when the current flows and immediately stops being a magnet when the current is lost. So the system is either deadbeat, that is, when we say deadbeat, that is critically damped, or it could be ballistic, which means the damping is as small as possible. So it depends on what someone wants, either critical damping or um, that the damping is as small as possible, maybe it is lightly damped, and so on and so forth. So with reasonable light damping, the period is unchanged, but as the damping is increased, the oscillations die away more rapidly. So if the damping is light, the frequency and the period remains constant, as we have seen in our previous illustrations. The frequency, that is the number of oscillations, would remain constant if the damping is light. But if the damping is increased, then the period may start. You may find that the period starts decreasing, and if you continue increasing the damping with time, you may just find that there is no oscillations, but just the system, the oscillations die away more rapidly, resulting into what we shall call critical damping. I think I illustrated a moving coil meter here, even though it's not part of this curriculum. I was trying to show what is really inside a moving coil meter, such as an ammeter or a voltmeter, which uses analog. So as current flows through we have an electromagnet which is created, which moves the pointer immediately. And when the current is lost, the pointer immediately moves back to zero. That is for a moving coil galvanometer or a moving coil meter or an analog meter which uses a pointer. So this pointer here is damped by an electromagnet. So that is one application of damping, basically critical damping. Okay, so a few things we need to say more about damping. Damping reduces total mechanical energy of the oscillating system and thus reduces the amplitude. That one you should note it very carefully. When the system is damped, the amplitude of oscillation decreases simply because damping reduces the total energy, which we are calling the mechanical energy or the energy of the oscillating system. Now you may be asking yourself, therefore, can we maintain the amplitude of an oscillator? Of course not. We cannot really keep the amplitude constant. So what we were mentioning in simple harmonic motion were just approximations. We cannot keep the amplitude of an oscillator constant. We can't maintain it. But then, can we increase the amplitude of oscillations indefinitely. Indefinitely means forever. Of course, still no. We cannot increase the amplitude of oscillations indefinitely. So what is this taking us to? Then, because you cannot displace somebody on a string and you increase their amplitude indefinitely, and their amplitude increases indefinitely, it means something has to be done if one, we want to maintain the amplitude of the oscillator for some time, not indefinitely, but for some time. And if we want to maintain the amplitude of vibration or oscillation of an object for some time, then this takes us to what we are going to call forced oscillations. So we have talked about free oscillations, no loss or gain in energy, amplitude is constant. We have talked about damped oscillations. There is a decrease in amplitude because of dissipative forces which are using up the energy. And lastly, I want us to talk about forced oscillations. So let's talk about forced oscillations. What do we mean by forced oscillations? At the start of the lesson, I gave you an example of a car engine. I gave you an example of a car engine when a car engine is started and when a car engine is started and your body starts vibrating. So many objects can be forced to vibrate. If you sit in a bus, you may notice that the vibrations from the engine are transmitted to your body, causing you to vibrate with the same frequency as the engine of the bus. These are not really free vibrations of your body because the engine of the bus is actually the one forcing you to vibrate. These are vibrations of the engine which are causing your body to vibrate. Therefore, the frequency with which your body is vibrating is not the natural frequency of vibration of your body. However, you are vibrating at the frequency of the engine of the bus, so we shall call it the forcing frequency or forced frequency or the driving frequency. So, forced oscillations occur where continuous input of energy is done so that the system which is able to vibrate can be made to vibrate for a specific period of time. That is what we are calling forced oscillations. So a system which is capable of vibrating is subject to an external periodic force to set it oscillating for the required time. For example, if you blow air in a pipe, the moment you stop blowing air in a pipe, the sound stops coming out of the pipe. Because you were blowing air in the pipe, you were forcing the air molecules in the pipe to resonate. So forced oscillations are vibrations that are driven by a periodic external driving force. Vibrations or oscillations that are driven by a periodic external driving force. Those are what we call forced oscillations. A continuous input of energy is required to keep a system vibrating for the required period of time. Those are the ones we are going to call forced oscillations. So, as a simple example of forced vibrations is a child's swing. As you push it, the amplitude increases. If you stop pushing it with the time, the amplitude will decrease. Another example is a loudspeaker. A loudspeaker is also an example of forced oscillations. It's made to vibrate by the force on the magnet on the current in the coil fixed on the speaker cone, on the loudspeaker cone. If the current stops flowing, um, the force on the magnet stops and therefore the cone stops vibrating. Those are forced oscillations. I've also talked about engines, the engine vibrations making bus windows to oscillate or making your body to vibrate when you are inside a bus. When there is an earthquake, the earthquake can make buildings to vibrate. When the earthquake stops, the buildings stop vibrating. Those are forced oscillations. So forced oscillations in a nutshell occur when a system is made to oscillate at the frequency of another vibrating system, that causes it to vibrate, that gives it additional momentum to oscillate continuously. A system which is capable of oscillating is made to oscillate at the frequency of another vibrating system that causes it to vibrate, or that gives it additional momentum or additional energy to oscillate continuously. As soon as that system, which is forcing, or the driving system, stops vibrating, the other system that is being forced to vibrate also stops. That's what we call forced oscillations. And we have given some examples. I want to illustrate some of them, even though they are not part of the exam. Some examples I talked about the moving coil loudspeaker. The cone of a loudspeaker is connected to a magnet and a coil of wire, which coil of wire becomes a magnet when there is a current, or creates a magnetic field around it when there is a current flowing through it. And because it's an alternating current which flows through the coil, this keeps changing direction. So the magnetic field around also keeps changing direction, which is able to make the cone to vibrate in and out depending on the direction of the magnetic field. So this is an example of forced oscillations. So by varying the electric current through the wires around the electromagnet, the electromagnet and the speaker cone can be made to move back and forth. That is, they are being forced to vibrate. That is a forced oscillations. If the variation of the electric current is at the same frequencies of sound waves, that is, for example, the frequencies detected by the human ears are between 20 hertz to around 20,000 hertz. So if the variation of the electric current, that is the number of cycles it makes per unit time, that is the frequency of the alternating current, if it is the same as the sound waves, then it means the cone is going to be vibrating with the frequency of the sound waves, which can be detected by the human ears. These include that from the voice and music. That's what we call forced oscillations. So the cone of the loudspeaker is forced to vibrate in and out. As it vibrates, it causes sound waves which propagate through air around up to our ears, which caused our eardrums to also vibrate in order for us to be able to detect the sound which is being produced. So those are called forced uh, oscillations or forced vibrations. I've also talked about a child on a swing, for example. A child on a swing is an everyday example of forced oscillations. When the swing is displaced and released, it oscillates with its natural frequency. But if we want to keep it oscillating for a certain period of time, we must continuously push the person on the swing. Due to damping, the amplitude of oscillations would decrease. But because we want the swing to continue oscillating for the required period of time, then we must continuously apply energy. So to keep the amplitude constant, the driver must push at the right time that the swing is about to swing downwards, as shown by this animation here. So the person pushing is going to be the driver system, and the person being moved is going to be the driven system. The driver keeps on providing energy to the oscillating system to keep it oscillating for the required period of time. The frequency with which this person on the swing would move, if he was free without someone continuously pushing, would be called the natural frequency. But because the person is continuously being pushed, the frequency with which they are oscillating is going to be called the forced frequency. So the frequency at which an object is made to vibrate by another system is called the forced frequency. So now you know the difference between a natural frequency and forced frequency. For natural frequency, the frequency with which an object oscillates if it is free to do so with no loss or gain in energy. Then for forced frequencies, the frequency at which an object is made to vibrate by another system. The frequency at which an object is made to vibrate by another system. That is what we call the forced frequency. The frequency at which an object is made to vibrate by another system. That is what we call the forced frequency. Okay. So let's try to understand first oscillations in more details. So when the frequency of the driver is the same as the natural frequency of the driven oscillator, what really happens at that point? The oscillator, which is now the other person who was seated on the swing, would absorb maximum energy from the person who was pushing. And remember, energy of an oscillating system is given by a half m omega squared times x naught squared. We are saying that when the frequency of the driver is the same as the natural frequency of the driven system, what happens to the driven system? The driven system is going to absorb maximum energy from the driver. And if the system absorbs maximum energy, what happens to the amplitude? The system will vibrate with maximum amplitude. But remember, we have already mentioned that damping or resistive forces limit the maximum amplitude. And if the velocity is low, or the speed of vibration or the speed of oscillation is low, we have also mentioned that damping force is proportional to the speed. But for high speed, the damping force is proportional to the speed squared. I think we have mentioned this in AS. If the car is moving slowly, you notice that the air resistance may be directly proportional to the speed if the car is moving slowly. But if the car starts speeding up, you notice that force due to air resistance will now be directly proportional to the speed squared. In other words, the force to air resistance now increases more rapidly as the speed increases. That is, if the speed is increased. So for low velocity, the damping force, which could be friction, which could be air resistance, is proportional to the speed in that case. But for high speed, the damping force, which is the resistive force, is proportional to the speed squared. You mentioned that in AS. What does that imply? It means that more energy needs to be provided by the driver to increase the amplitude of oscillation further when there is damping. So if there is damping as you push someone on the swing, then you'll be required to give in more energy or to use more energy to increase the amplitude of oscillations further. If there is damping, more energy is going to be required. But remember I said when the frequency of the driver is the same as the natural frequency, the driven oscillator would absorb more energy. And if the energy absorbed is more, it means the amplitude of oscillation is going to be larger. And this is going to lead us to a concept that we are going to call resonance. So a driven system is going to absorb maximum energy from the driver system when the two frequencies are matched. Imagine you are pushed on a swing and left to oscillate on your own, and you oscillate at your natural frequency. But then you have your natural frequency if you were to oscillate on your own, but then then a driver system acts on you when you are on the swing. And it happens that the frequency of the driver matches your natural frequency if you were free to oscillate on your own. It means you who is oscillating will now obtain maximum energy from the person who is pushing you. And what happens if you obtain max or absorb maximum energy? You'll oscillate with the maximum amplitude. That's what we are going to call resonance later on. Okay, so let's explore forced oscillations in comparison to resonance, or forced oscillations and resonance. Having seen that for forced oscillations, a system which is capable of oscillating is subjected to a periodic force to give it continuous momentum or energy so that it oscillates for a required period of time. So let's explore what we mean by resonance. So having seen that forced oscillations or a forced oscillation occurs when a body is made to oscillate by application of a periodic driving force. This force is applied at regular intervals as we demonstrated with a swing. The force is applied at a specific regular intervals as we demonstrated with the swing. But I mentioned we have two systems here, the driver system and the driven system. The driven system, just like any other object, has its own natural frequency. The driver system has a frequency which we call the driver frequency or the forcing frequency. The moment the forcing frequency matches with the natural frequency of the driven system, I mentioned that the driven system absorbs maximum energy and is going to therefore oscillate with maximum amplitude. And that's what we are going to call resonance. So at resonance, the frequency of the periodic driving system or driving force, which is applied at regular intervals, is going to match or is going to be equal to the natural frequency, which we are going to call F naught, of the body being forced to oscillate. What is the impact? The impact is going to be that the oscillator or the object being forced to oscillate will absorb maximum energy. And if energy is directly proportional to the amplitude squared, it means it oscillates with the maximum amplitude. So the driving force supplies the energy for the oscillator to vibrate with the maximum amplitude. The driving force, which is applied at periodic time intervals, is now going to supply maximum energy to the oscillator, and the oscillator is going to be forced to vibrate with the maximum amplitude, and this is what we are going to call resonance. So the examiner will ask you to explain what you understand by the term resonance. So resonance occurs when the natural frequency of vibration of an object or system is equal to the driving frequency. What is the impact? It resulting into maximum amplitude of vibration. The natural frequency equals to the driving frequency, resulting into maximum amplitude of vibration. Now, this frequency, the periodic frequency, I mean the frequency of the driving force or the driving system, which matches the natural frequency of a body, is what we shall call the resonant frequency. The frequency of the driving system, which perfectly matches the natural frequency of a given object or the driven system, is what we shall later on call the resonant frequency. So this is what we call resonance. Resonance occurs when the natural frequency of vibration of an object is equal to the driving frequency, resulting into maximum amplitude. I have explained why there is maximum amplitude. When the natural frequency is equal to the driving frequency, the object which is being driven absorbs maximum energy. And because energy is directly proportional to amplitude squared, it means there is going to be maximum amplitude. So if we increase the driving frequency, so let's say the natural frequency of a system is 20 Hertz. This is the natural frequency. I'll call this one F naught. And then we can now increase the driving frequency, which I'm going to call FD, from say 0 up to, let's say, up to 40 Hertz. So we increase the driving frequency. As we increase the driving frequency, of course, the amplitude of oscillation starts increasing because the system starts absorbing more and more energy. When we reach 20 Hertz, we are increasing the frequency of the driver. The moment we reach 20 Hertz for the driver, the driven system absorbs maximum energy and vibrates with the maximum amplitude. Unfortunately, the moment we exceed this one and say go to 30 and so on and so forth, if we go beyond, if the frequency of the driver exceeds the natural frequency of oscillation, again the amplitude of vibration decreases. You can try this when you are pushing someone on a swing. If your hands move in the same direction as the swing, you'll always push that person to a higher point because the natural frequency is going to be matching with the natural frequency is going to be matching with the forcing frequency. But if you move your hands faster to push the person, the amplitude will instead decrease, because it would mean the driving frequency has exceeded the natural frequency of vibration. So in that case, the amplitude decreases, which means if I try to sketch a graph, of amplitude against frequency for a driven for an object which is being forced to oscillate, then the graph would look like this. If the driving frequency is increased slightly, the system which is being driven absorbs more and more energy and vibrates with maximum amplitude. So if we increase the driving frequency beyond the natural frequency of vibration, then the amplitude is going to be decreased, the amplitude is going to be distorted. The system instead loses energy to the driver. If you push the person faster than the string is moving, it means your hands are oscillating. The movement of your hands is higher than the string itself, which means you'll instead take out energy from the oscillating system. In other words, the amplitude therefore decreases. This is what we call the resonance curve. The amplitude is maximum at a certain frequency f naught. So here, the driving frequency is the same as the natural frequency. And f naught is many times going to be called the resonant frequency. What is the spelling of resonant? I think it just ends with e, resonant frequency. So at this point here, where the driving frequency is equal to the natural frequency, that driving frequency, which is the same as the natural frequency, is called the resonant frequency. The driven system absorbs maximum energy from the driver system and therefore oscillates with the maximum amplitude. So if I sketch a graph of amplitude against driving frequency, so let's say the driving frequency increases from 0. The moment it reaches f naught, the system absorbs maximum energy. The moment the driving frequency exceeds x naught, then the amplitude decreases. And I'm saying this is called the resonance curve. So I want you to note a few things from this curve. Number one, note that the maximum amplitude is achieved when the frequency matches the natural frequency of the oscillation. When the driving frequency matches the natural frequency of oscillation. Number two, when you look at the peak is not infinite. What I mean by infinite, the peak is not very sharp. What does that mean? It's like there is a range of frequencies for which the amplitude is almost maximum. There's a range of frequencies for which the amplitude is almost maximum. That range of frequencies can only be explained by the fact that there could be damping, because if there was no damping, then the amplitude would just rapidly go to maximum and rapidly go to minimum if there was no damping. But because there is damping, we have a range of frequencies for which the amplitude is almost maximum. So the fact that the peak is not infinite, it's not sharp, is evidence of damping being present. So from the resonance curve, we can see that there is damping if the peak is not sharp as expected, if the peak is not infinite as expected. So this curve is showing that there is damping, that's why it's not very sharp. This curve is not very sharp, which indicates that there must be damping, which is causing some loss in energy, thereby affecting the amplitude, thereby affecting the frequencies for which the amplitude is maximum, making the frequency not to be a single value frequency, but it's almost it's almost a small range of frequencies for which the amplitude is maximum. So that's what we call the resonance curve. Suppose we increase the damping. Maybe here there is light what? This is for light damping. For light damping, that's what we expect. the amplitude is maximum, but the peak is not very, very sharp. Suppose we now increase the damping maybe to heavier damping, critical damping, and so on and so forth. We go on increasing damping. What happens? Of course, if there was no damping, we would expect this to be very sharp. If there was no damping, we would expect something like that. But if this is light damping, here there is no damping. So it means if we increase damping, maybe we go to heavy damping. If we have heavy damping, of course, damping leads to loss of energy. It means more energy is being lost. So the amplitude is going to be lower. There is going to be a smaller amplitude. And the peak is actually going to be the amplitude of oscillation at all frequencies is going to be reduced. And of course, the frequency at which maximum amplitude occurs is going to shift to smaller values is going to shift to smaller values. In other words, we may have a graph which is like this. First of all, the peak is going to be to the left of the first one. If damping is increased, the peak is going to be to the left of the first one. This is for heavy damping. The peak shifts to smaller values, and the amplitude for all values of frequency is going to be decreased. Okay, so let's discuss resonancy and damping in details. So we have seen the resonance curve. Let's now discuss resonancy and damping. So first of all, if there was light damping, this is what we would expect. One, the amplitude of the first oscillation depends on the comparative values of the natural frequency and the driving frequency. As the degree of damping increases, it is seen that number one, the amplitude at all frequencies the amplitude of oscillation at all frequencies is going to be reduced, because remember, damping results into loss in energy, and energy is directly proportional to x naught squared. So as the energy decreases, the amplitude also decreases. That is obvious. Number two, observations show that the frequency at maximum amplitude shifts gradually towards lower frequencies. In other words, the peak shifts to the left-hand side. And by the way, the peaks also become flatter. Because of damping, as we have more damping, then we shall have a wide range of frequencies for which the amplitude is maximum. So the peak becomes flatter as demonstrated by these peaks here. So if damping was to be increased even further, then we would have something like this. So the peak will have a wide range of values, so it becomes even more flatter. So as damping increases, the peak becomes flatter. The peak shifts to smaller values of frequency, that is, shifts towards lower frequencies. And of course, the amplitude of oscillation at all frequencies is going to be reduced. So that is if damping is increased. If damping is decreased, then the peaks become sharper. In other words, the peak becomes infinite, as shown by the green peak here. If damping is decreased or reduced, the peaks become sharper and sharper, and the peaks will therefore shift to the right-hand side if damping is decreased. So you should be able to understand that there is damping when resonancy occurs. So that is resonancy and damping. You should be able to explain the resonant curve. You should be able to explain the features of the curve. You should be able to explain what happens to the features of the curve when damping is increased or when damping is decreased. And I've showed you what happens when damping is increased. First of all, if damping is increased, the amplitude of oscillation decreases. The frequency at maximum amplitude shifts to the left-hand side. In other words, shifts to lower values, or the peak shifts to the left. And of course, the peaks become flatter or it becomes broader. In other words, there will be a wider range of frequencies for which for which the amplitude is almost maximum. That's what we call damping and resonance. A few things we need to note from resonance and damping. The the sharpness of the resonance curve depends on the amount of damping being very sharp for light damping. So if we have only light damping, it is going to be very sharp. If there is completely no damping, it will be infinite. It will be something like that. That is what we call infinite, very sharp. So that there is only one frequency for which the amplitude is maximum. For example, damping is, by the way, useful if we want to eliminate or reduce the effect of resonance. Because we have seen that resonance makes the system to absorb maximum energy and vibrate with maximum amplitude. Suppose we are not interested in a system to vibrate with maximum amplitude, then damping is going to be useful. A good example is given with shock absorbers. Imagine if shock absorbers were not damped, then it would mean if resonance occurred, then the car would easily overturn. So whenever we want to ignore or to overcome the effect of resonance, then damping might be useful. A good example is in countries where they experience a lot of earthquakes, such as maybe Japan. During earthquakes, buildings are forced to oscillate by the vibrations of the earth, and resonance could occur, which would result in serious damage. In countries where earthquakes happen regularly, buildings may be built on foundations that absorb the energy of the shock waves. That is, these are called damped foundations. In this way, the vibrations cannot reach dangerous levels. Of course, this is going to be very expensive, but of course, it is only common in wealthier countries. So, in wealthier countries, the effect of resonance could be experienced if an earthquake occurs. So, if we are sure that an earthquake would occur, and of course, we are sure that resonance would also occur, then why not come up with strategies to overcome the effects of resonance when when an earthquake occurs, such as constructing houses onto damped foundations, where during an earthquake, the foundations can absorb the shock waves of the earthquake. So this calls for damping. So whenever we want to ignore the effect of damping, then whenever we want to ignore the effect or to overcome the effect of resonance, then damping could be necessary. For the teachers, you can demonstrate damping in the laboratory with what we call Barton's pendulum, where you can come up with at least 4 paper cones and a simple pendulum or pendulum bob, and make sure that the lengths of the pendula are different, apart from one pendula which has the same length as the pendulum bob. And displace the pendulum bob as illustrated in this diagram and observe what happens. If you recall from simple harmonic motion, we saw that the period of oscillation of a simple pendulum, I think, was given by 2 pi square root of L divided by G. In other words, the period of oscillation of a simple pendulum was not dependent on the masses. So even if these are light paper cones and this is a heavier pendulum bob, the period is directly proportional to the square root of L. What does that mean? C will have the same period as the pendulum bob. In other words, C will have the same period as the pendulum bob, and remember frequency is equal to 1 over T, so it means C and X will have the same frequency. That means there is a high possibility that C will oscillate with the maximum amplitude because its natural frequency can easily be equal to the driving frequency of the pendulum bob. So this can demonstrate what we mean by resonance. So have paper cones attached onto strings and fixed on 2 clamps as shown in this diagram. Then displace the pendulum bob only. Of course, E, D, C, and B up to A will absorb energy and they will start oscillating. But in the laboratory, you will observe that it is C which is going to absorb maximum energy because it has almost the same length as X and therefore to have almost the same period and will end up having the same frequency. Therefore, resonance will occur for C. So this apparatus is used to demonstrate resonance. It is called Barton pendulums. It consists of a set of light pendulums and more massive pendulum, which is called a driver. I call it X. All of these are supported by taut strings. They are supported on a taut string. And when pendulum X is displaced, all the other pendulums starts moving, but they start moving at different frequencies. The pendulum, which has the same length as X, will oscillate in phase with large amplitudes. So it will oscillate in phase with X and with a large amplitude. So pendulum C, for example, has the same length as the driver X. So it would have the same natural frequency as the driver, and therefore it will have the same period as the driver. It will absorb maximum energy from the driver and it will vibrate with the maximum amplitude as compared to E, D, B, and A. So we say C is undergoing resonance, it is resonating. So you can demonstrate this in your classroom using what we call Barton's pendulum. These are easy to come up with in a classroom. If you can't do that, you can follow this link and um, watch the video. Okay, so we have talked about types of oscillations. We have talked about free oscillations, forced oscillations, damped oscillations. We have talked about types of damping, light damping, critical damping, heavy damping, and we have talked about resonancy, but we have also talked about the importance of damping if we want to overcome the effect of resonance. But one thing we need to note is that resonance also has applications in everyday life. Let's explore the applications of resonance. Benefits or applications of resonance. Number one, and this is going to be on a lighter note, we have what we call musical instruments. Musical instruments, such as especially the wind instruments, rely on concepts of resonance. Resonance is made use of in, let's say, musical instruments rely on resonance to amplify the sound produced. Wind instruments are sounded by making a column of air resonate by blowing a whistle at one end. So when you blow air at one end of let's say a windpipe or a musical instrument that uses wind, you'll cause the air inside the windpipe to resonate. Talk about strings. Stringed instruments like guitars have a hollow wooden box with a hole under the strings, which act in a similar way. To amplify all notes from all of the strings, the sounding box has to be a complex shape so that it resonates at many different frequencies. So we are saying musical instruments rely on resonance to amplify the sound produced. I've mentioned wind instruments where you have to blow air to make the air which is already inside to resonate. I've talked about stringed instruments like the guitars, which have a hollow wooden box with a hole under the strings, which act also in a similar way. And to amplify all notes from all of the strings, the sounding box has to be a complex shape so that it resonates at many different frequencies. So musical instruments rely on resonance. I don't expect any student to write this as an answer in an exam. It is really very light because there are better applications of resonance, such as resonant vibrations of the quasicrystals are used to control clocks and time. Resonant vibration of quasicrystals are used to control clocks and watches. We shall talk about the quasicrystal in medical physics, especially ultrasound. But a quasicrystal vibrates or is made to vibrate at certain frequencies. And at those frequencies, it can control clocks. Its vibrations can control clocks because the quasicrystal is able to vibrate if there is an alternating PD across it. And the frequency of the alternating PD can be used to control the frequency at which the quasicrystal vibrates in order to control clocks and watches, which would be determining time. So resonance can be used in that case. The most common application of resonance at home, I think, is microwave oven cooking. Microwave oven cooking is a common application of resonance at home. How is this possible? How is microwave oven cooking using resonance? So the microwaves used have a frequency that matches the natural frequency of vibration of water molecules. So the microwave is the driver system, the water molecules is the resonating system. So what happens is that the water molecules in the food are forced to vibrate and they absorb energy of the microwave radiation. So the microwave is the driver, the water molecules is the resonating frequency. So the water molecules in the food are forced to vibrate and they absorb energy of the microwave radiation. So when resonance occurs, the water gets hotter and absorbs energy which spreads through the food and cooks or heats it up. That is application of resonance in microwave oven cooking or warming up of food. Then one other common application I think is in MRI, that is magnetic resonance imaging. Even though we are no longer studying magnetic resonance imaging in paper form, but MRI is a good application of resonance in medicine, especially to produce images of patients' internal organs. So here in MRI, we have what we call radio waves, which have a range of frequencies and they are being used in the imaging process. And particular frequencies from the range of radio frequencies are absorbed by a particular atomic nuclei in the body or in the patient's body. The frequency absorbed depends on the type of nucleus and on its surroundings in the body. And by analyzing the absorption of the radio waves, a computer-generated image can be produced. That is the basic application of resonance in MRI. So several radio frequency radiations are absorbed in the body, and the frequencies absorbed will depend on the type of the nucleus and its surroundings. So if we analyze the absorption of the radio waves by a computer, an image of a certain part of the body can be generated. One last and important application of resonance, I think, is going to be a radio or television also depend on resonance for tuning circuitry. So tuning circuitry of radio and TVs also rely on resonance. Tuning circuits of radios and TVs rely on resonance. By the way, you can be able to listen to a different radio station even when all of you are in the same room. Each of you can listen to a different radio station because of resonance. So the antennas or the areas will pick up signals of many different frequencies from many transmitters reaching your house, for example. However, the tuner can be adjusted to resonate at the frequency that you want or the frequency of the transmitting station you are interested in. So this makes therefore the circuit to resonate at a certain frequency you are interested in, which means the circuit is going to produce a large amplitude signal for that particular frequency only. It doesn't mean that all the other frequencies have not reached your radio. They have reached the circuit, but you have tuned it to a certain frequency to make the circuit resonate at that frequency only with the highest amplitude, leaving the others lower and not to be detected. So that is resonance. By the way, resonance could be troublesome. Even though this may not be examinable, resonance could be troublesome. Even though it is used to control clocks and watches using vibrating quasicrystals, even though resonance is important in microwave oven cooking, even though resonance is important in magnetic resonance imaging and tuning circuits of radios and TVs, resonance could be troublesome. How is resonance troublesome? I'll give you some everyday scenarios in which resonance has been troublesome. So, why do marching troops need to break a step when crossing certain suspended wooden bridges? Of course, we know that failure to do so caused the loss of over 200 French infantrymen in around, I think it was 1850. Because if they don't break step, they are most likely going to cause a driving frequency which matches the natural frequency of the suspended wooden bridge. And this would cause resonance, and the bridge would oscillate with the maximum amplitude, leading to a collapse. And that's what happened to the French infantrymen in 1850. Opera singers, by the way, can shatter wine glasses by forcing them to vibrate at their natural frequencies. You might have observed this somewhere, maybe on YouTube. An opera singer can shatter a wine glass by just forcing the glass to vibrate at their natural frequencies. If the frequency of the opera singer matches the natural frequency of the glass may vibrate with maximum amplitude and then it shatters. Of course, it is common for us to note that buildings can collapse in case of earthquakes because resonance increases the amplitude of vibration. Because resonance is troublesome, resonance in a car suspension needs to be damped. In case it is not damped, or in case there are no shock absorbers, then it means the car would go out of control. So if the dampers or shock absorbers are not working properly, the car would go out of control. If you run over a bump, the car would continue oscillating indefinitely if damping is not put in place. Resonance in car engines and generators can lead to components cracking or disintegrating with dangerous consequences. So we need to overcome the effect of resonance, perhaps by damping, because if it is not dealt with, car engines, generator components can crack and also disintegrate. This could lead to dangerous consequences. So the operation of the engine of a vehicle causes a periodic force on the parts of the vehicle, which can cause them to resonate. For example, at particular frequencies of rotation of the engine, the mirrors may resonate. To prevent excess vibrations, the mountings of the mirrors provide damping. So in good cars, the mountings of the mirrors provide damping because the designers expect that there is a possibility of resonance to occur, which could cause the mirrors to get scattered, to get destroyed. So the mirrors are fitted with dampers because they know the resonance effect could lead to their destruction. Another consequence of resonance can be seen in what we call the Tacoma Narrow Bridge. This, I think it was around 1940, the Tacoma Narrow Bridge. You can try to research about the Tacoma Narrow Bridge. The Tacoma Narrows Bridge disaster of 1940 was caused by the bridge being too slender for the wind conditions in the valley. One day, strong winds set up twisting vibrations and the amplitude of vibration increased due to resonance until the bridge collapsed. So here I've given a review of the original Tacoma Narrows Bridge opened on July 1st, 1940. It received its nickname "Galloping Gertie" due to the vertical movement of the deck observed by construction workers during windy conditions. The bridge collapsed into Puget Sound the morning of November 7, 1970, under high wind conditions. Engineering issues as well as the United States' involvement in World War II postponed plans to replace the bridge for several years until the replacement bridge was opened October 14th, 1950. Internet source is where I got this information here. And I gave a simple animation, a simple captured image of the Tacoma Bridge, how it used to appear during on windy days. So the original Tacoma Narrow Bridge at all stages of its short life was very active in the wind. You could see it dancing like this, the way you see this image here. Its nickname of Galloping Getty was earned from its vertical motions in even very modest winds, as you can see besides. So this, I don't know whether this is visible, but this is how it could behave. This is how it used to be, even in modest winds. Its collapse on November 7th, 1940 attracted wide attention at the time and ever since, due in part to its capture on film. So this was how it would be even in modest winds. Now imagine a situation when the wind is strong enough and the natural frequency of the bridge matches the frequency of the wind. Of course, it had to oscillate with maximum amplitude. So the bridge's collapse had a lasting effect on science and engineering. In many physics textbooks, the event is presented as an example of elementary forced resonance, with the wind providing an external periodic frequency that matched the natural structure frequency, though its actual cause of failure was aeroelastic flutter. So for them, science believe due to the external periodic frequency that matched the natural frequency, it must have contributed to the collapse of this bridge. Although some science believe it was due to elastic flutter. Its failure also boosted research in the field of bridge aerodynamics, aeroelastics, the study of which has influenced the designs of long-span bridges built ever since 1940. So today, the bridges built are really technically different. They are really different. Okay, so it means resonancy could therefore be troublesome, and sometimes overcoming it could be very, very, very necessary. So we have seen in a nutshell, we have summarized oscillations. We have come to the end of simple harmonic motion and oscillations. These chapters move together. We have really tried our level best to explore all these parts of these parts of oscillations. So in oscillations and simple harmonic motion, we have explored everything that is necessary. We talked about forced oscillations, damped oscillations, dissipative forces involved. We have talked about resonancy. We have defined simple harmonic motion. We have defined an oscillation, angular frequency or angular velocity, and so on and so forth. However, in this particular lesson of oscillations, we talked about the types of oscillations, where we talked about forced, free, and damped. We talked about damped oscillation, free oscillations being in the absence of dissipative forces, there was no loss or gain in energy. We have talked about a natural frequency of oscillation, that is a frequency of a body when it is free to do so with no loss or gain of energy. We talked about damping as the loss of energy due to dissipative forces leading to a decrease in amplitude. We distinguished between the three types of damping: critical, we talked about heavily damped and light damping. Then we talked about forced oscillations and forced frequency, where we came up with the resonancy. We explored the resonance curve and we were able to see the benefits of resonance, which included the magnetic resonance imaging, microwave oven cooking, tuning circuits of radios and TVs, vibrations of the quasi-crystal to control watches and clocks, amplification of sound in musical instruments, and many more. We ended this lesson by exploring some troublesome aspects or situations of resonance, where we saw some things which happened, and the most eye-catching one is the Tacoma Narrows Bridge the Tacoma's Narrow Bridge, which collapsed in 1940. That disaster awakened the minds of several engineers so that for the bridges which were constructed after 1940, either they were damped or several things were put in place to prevent the effect of resonancy, or several things were put in place to prevent the effect that would lead to the collapse of the bridge. And I think that leads to the end of the concepts of oscillations. Until next time, bye bye.